Hi friends, here I am going to present session number 6 of paper 7 analysis 2 and algebra 4 of 6th semester mathematics. The topic is analytic function. So this is a new term. This is not came in real functions. So we didn't heard this term analytic function in case of real functions. So only in case of complex functions we have to define analytic function. So let us see what is analytic function. So we define analytic functions using differentiation, using differentiability. So let us see the definition of analytic function. A function that is a complex function f of z is said to be analytic at a point z0 if it is differentiable at z0 and also at every point of some neighborhood of z0. That is, a function that is a complex function f of z is said to be analytic at a point z0 if it is not only differentiable at z0 but also at every point of some neighborhood of z0. That neighborhood means it is around z0. The points are around z0. All the points around z0, that is less than z0 or greater than z0. Analytic function is also called as regular function or holomorphic function. A function f of z is said to be analytic in a domain D. That domain means it contains some points if it is differentiable at every point in D. So, function is analytic in a region D, then it is differentiable at every point in D. So, now let us see some necessary condition for analytic function. So, the necessary condition is given in terms of an equation that is called Cauchy-Riemann equations. So, Cauchy-Riemann equations are nothing but the partial derivatives satisfying dou u by dou x is equal to dou u by dou y and dou u by dou y is equal to minus dou u by dou x. So, these equations are called Cauchy-Riemann equations. We know that complex function is represented by u of x comma y plus I into v of x comma y, that is u and v are functions of x and y. So, there the derivatives involved are partial derivatives. If there is a function of more than one variable, there we have to find partial derivatives, not the ordinary derivatives. So, this function is said to be analytic in a domain D if u and v satisfy the equations, that is dou u by dou x is equal to dou u by dou y and dou u by dou y is equal to minus dou u by dou x. So, these equations are called Cauchy-Riemann equations and these conditions is called necessary condition. So, this condition is that Cauchy-Riemann condition is called necessary condition. If a function is analytic, then it satisfies Cauchy-Riemann equations. Let us see the necessary condition in terms of a theorem. If f of z is equal to u plus iv is analytic in a domain D, then u and v satisfy the equation, that is Cauchy-Riemann equations. Dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. So, as in the previous slide, we know that the definition of analytic function. So, the function is analytic means it is differentiable, that is its derivative exists. So, let f of z be analytic, that implies f dash of z is equal to limit of f of z plus delta z minus f of z divided by delta z, as delta z tends to 0 exists and this limit is equal to unique. Now, we have to substitute f of z plus delta z and f of z delta z in terms of u, v, x, comma, y. Now, f of z is equal to u of x comma y plus I into v of x comma y. So, delta z is delta x plus I delta y. Therefore, f of z plus delta z, that is change in delta z, leads to the change in x and change in y. X plus delta x, y plus delta y plus I into v of x plus delta x comma y plus delta y. Now, we have to substitute these things in the differentiability, that is f dash of z, that is in the limit as delta z tends to 0. So that is u of x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y minus of f of z, that is u of x comma y plus I into v of x comma y divided by delta x plus I delta y. So here the limit as delta z tends to 0. So delta z tends to 0 means delta x tends to 0 and delta y also tends to 0. So here we consider two cases. So the case first is if delta z is purely real. Purely real means there is no imaginary part. The imaginary part is 0. That is delta y is equal to 0. Then delta z is equal to only delta x. Now substituting this limit f dash of z is equal to limit as delta x tends to 0, that is u of x plus delta x comma y. So delta y is 0, so we have y plus I into v of x plus delta x comma y minus of u of x comma y plus I into v of x comma y. So there is no change, we keep as it is, that we keep the terms as it is, so that we get on separating real and imaginary parts f dash of z is equal to limit as delta x tends to 0 u of x plus delta x minus u of x comma y. So here we have to collect u terms together and v terms together, that is we separate real parts and imaginary parts. So the real part is u of x plus delta x comma y minus u of x comma y divided by delta x plus I into v of x plus delta x comma y minus v of x comma y divided by delta x. So this limit is equal to dou u by dou x. So here we change x keeping y constant. So it is a derivative with respect to x keeping y constant. So it is dou u by dou x. And the second part is the derivative of v with respect to x keeping y constant. So we get dou u by dou x. Here f dash of z is equal to dou u by dou x plus I into dou v by dou x. Similarly, we find the derivative f dash of z in the second case. So that is if delta z is imaginary, if delta z is purely imaginary. So purely imaginary means the real part delta x is equal to 0. So only we have delta y, that is delta z is equal to I delta y. Now f dash of z is equal to limit as delta y tends to 0. So we put delta z is equal to I delta y. Delta z tends to 0 implies delta y tends to 0. So here x is constant, that is delta x 0. So we have only u of x comma y plus delta y plus I into v of x comma y plus delta y minus of, so keep same as it is same, divided by I delta y. So delta z is I delta y. And taking limit as delta y tends to 0. So here it is delta y, not delta x. Please replace this delta x by delta y, so that we get, so here we find the partial derivative u with respect to y. So here we changing y keeping x constant, so it becomes dou u by dou y and 1 by I plus I into, this is here also we change v with respect to y keeping x constant, so its derivative with respect to y dou v by dou y. Here I cancel. So next we write this 1 by I as minus I. If we take I to numerator, that is we multiply both numerator and denominator by I. So I square becomes minus 1, so it is minus I. So we write f dash of z is equal to dou v by dou y minus I dou u by dou y. So comparing equations 1 and 2, so in first equation we have f dash of z is dou u by dou x plus I into dou v by dou x. In second equation dou v by dou y minus I into dou u by dou y. So comparing we get, so left hand side is same. So similarly we have to equate the right hand side, and also the limit is unique. So dou u by dou x is equal to equating real parts and imaginary parts. Dou u by dou x is equal to dou v by dou y, and dou v by dou x is equal to minus dou u by dou y. So these are the Cauchy-Riemann equations, and this is the necessary condition for the analytic function. Here onwards, to verify, to prove any function, any complex function is analytic, we have to verify the CR equations, Cauchy-Riemann equations. Okay, let us see some examples on CR equations. Verify whether the real and imaginary parts W is equal to sin Z satisfies CR equations. So to verify CR equations, we need to find U and V. So we want U and V, real part and imaginary parts. For that, we take Z is equal to x plus iy. F of Z is equal to sin Z, that is equal to sin of x plus iy. It is sin of a plus b, sin a cos b plus cos a sin b, sin x cos iy plus cos x sin iy. So we know that cos iy is cos hyperbolic y and sin iy is sin hyperbolic y. Cos iy is cos hyperbolic y, sin iy is sin hyperbolic y. So here we have the real part u is equal to sin x cos hyperbolic y and imaginary part v is equal to cos x sin hyperbolic y. So find the partial derivative with respect to x, that is dou u by dou x is equal to cos x differentiation of sin x cos hyperbolic y, as it is dou u by dou x differentiation derivative of v with respect to x, differentiation of cos x is minus sin x sin hyperbolic y constant, keep as it is. And similarly find the partial derivative with respect to y, that is dou u by dou y is equal to differentiation of cos hyperbolic y is sin hyperbolic y, sin x sin hyperbolic y, dou v by dou y is equal to differentiation of sin hyperbolic y is cos hyperbolic y, so it is cos x cos hyperbolic y. So by observing here we get dou u by dou x is equal to dou v by dou y, cos x cos hyperbolic y, and dou u by dou y is just negative of dou v by dou x. So CR equation satisfied, hence the given function is analytic. Similarly, we have to see one more examples on this. To see one more example on this one, show that the derivative f of z is equal to cos z exists using CR equations and find its derivative. So you have to find the derivative using CR equations. Solution. So let f of z is equal to cos z. Again we have to write cos z in terms of u of x comma y plus I into v of x comma y. For that take z is equal to x plus iy. So it is cos of a plus b, cos a cos b minus sin a sin b. That is cos x cos iy minus sin x sin iy. Cos iy, as we know, it is cos hyperbolic y, and sin iy is I sin hyperbolic y. So here we get the real part u is equal to cos x cos hyperbolic y, and imaginary part v is equal to minus sin x sin hyperbolic y. So after finding u and v, you have to find the partial derivatives with respect to x and with respect to y. So here we get dou u by dou x is equal to minus sin x cos hyperbolic y, dou v by dou y, that is differentiation of cos x is minus sin x, dou v by dou x differentiation of sin x is cos x, so minus is there, you have to keep as it is. And similarly dou u by dou y differentiation with respect to y, that is cos hyperbolic y differentiation is sin hyperbolic y, and similarly here sin hyperbolic y differentiation is cos hyperbolic y. So by observing here we have dou u by dou x is equal to dou v by dou y, that is minus sin x cos hyperbolic y, and similarly dou u by dou y is minus negative of dou v by dou x. So CR equation satisfied, the function is analytic. So next we have to find the derivative of f of z, that is cos z. So what is the derivative of cos z? It is clearly minus sin z. Differentiation of cos z is minus sin z. So here we have to find by using CR equations. So in necessary condition, we know that the derivative f dash of z is equal to dou u by dou x plus I into dou u by dou x, that is equation 1. So using that equation 1, so this is very important. So here onwards you have to use this equation to find the derivative. To find the derivative, you have to write f dash of z is equal to dou u by dou x plus I dou u by dou x. So substitute dou u by dou x and dou v by dou x. We get minus sin x cos hyperbolic y plus I into minus cos x sin hyperbolic y. So on taking minus common, we have sin x cos hyperbolic y plus I into cos x sin hyperbolic y. So again we write this cos hyperbolic y as cos iy, I sin hyperbolic y as sin iy. So this is sin a cos b, cos a sin b. So sin a cos b, cos a sin b is sin of a plus b, that is sin of x plus iy. Sin of x plus iy is nothing but minus sin z. Similarly, we can find, so here the derivative of f dash of z is minus sin z. Differentiation of cos z is minus sin z. Similarly, we can show that in example 4, f of z is equal to log z is analytic, and hence we find the derivative of log z is 1 by z. So here also we have to find the real part and imaginary parts first. So let f of z is equal to u plus iv. So this f of z is log z. So on changing this log into indices form, exponential form, we write e to the power u plus iv is equal to z. This is a log z to the base e. So z is equal to e to the power u plus iv. Separating real and imaginary parts here, e power u plus I into e power iv. So on using Euler's formula, we write e power iv as cos v plus I sin v. And equating real and imaginary parts, we get x is equal to e to the power u cos v and y is equal to e to the power u sin v. So squaring and adding, we get x square plus y square is equal to e to the power 2u, or u is equal to 1 by 2 log of x square plus y square. Similarly, by dividing y by x, we get v is equal to tan inverse of y by x. So this is the imaginary part, and u is equal to 1 by 2 log of x square plus y square is the real part. So after finding u and v, you have to verify Cauchy-Riemann equations. So Cauchy-Riemann equations are verified, hence f of z is analytic. So finally we have to find the derivative. So to find the derivative, we have to use f dash of z is equal to dou u by dou x plus I dou v by dou x. So substituting dou u by dou x and dou v by dou x, we get x minus iy by x square plus y square. So we write this x square plus y square as x plus iy into x minus iy. So x minus iy cancel, only we have 1 by x plus iy. This is nothing but z 1 by z. So here f dash of z is 1 by z, that is the derivative of log z is 1 by z. So these are some examples on Cauchy-Riemann equations and analytic functions. Thank you.